will welcome you all in today's episode of Science Simplified only on Bharata First. Through this platform, we provide a unique opportunity to ask questions related to science and technology, which will be answered by the experts. Let your curiosity out and ask questions through a form whose link has been provided in the description box below. Do make use of this opportunity. Now, I would like to introduce to our science expert, Dr. T.V. Venkateshwaran, who is here with us to answer the questions sent to us by our viewers last week. Dr. T.V. Venkateshwaran is a senior scientist at Vigyan Prasar, New Delhi. He is also founder of India Science Wire. His area of research includes science, technology, and society. He also writes regular columns on the development related to science and technology. So, the first question for today is:
Hello everyone, this is Mehraj. I have done my bachelor's in science. Right now I am preparing for UPSC. My question is, what are carbon nanotubes? What are the applications of carbon nanotubes? And what future potential it holds? Thanks.
Important thing. I mean, it's one of the emerging new material that people are hoping to use in a big way. So, if I look at, for example, carbon, there are two forms of carbon that we are all very much aware of. One is, of course, diamond. The other is graphite, right? Whenever you are using a pencil, you are using graphite. Both are nothing but carbon. Okay, both are carbon, we know it. So when you arrange the carbon in a particular structure, that is in a very ordered structure, you get diamond. If you arrange them as layers, I mean, this is one layer, this is another layer, like that. I mean, if it is a sheet, like sheet by sheet, then you get graphite. Okay, so these are all two forms of carbon. Now I can make the carbon in different structures. Okay, I can give different structures. For example, if I take 60 carbon and arrange them like this, okay, arrange them in this kind of a fashion, then I get something called a C60 fullerene. It's a new form of carbon. Okay, if I take a graphite and one layer alone, I remove it, I get the graphene. If the carbon is unstructured, then it is amorphous. Instead of 60, I take 540 and construct a ball-like structure. Then I get C540 fullerene. So I can make different structures the way they arrange the carbon atom into a particular shape, and then whether in a 2-dimension or lattice, these kind of things, it brings in different forms of carbon. Okay, so if I take a carbon graphene sheet, okay, and then just roll it up, then I get a carbon atom. That's it. Okay, so when I roll it, I get a carbon nanotube. That's what is a carbon nanotube. A graphene is 2-dimensional, but whereas a carbon nanotube is 3-dimensional. Okay, so if I look at the carbon nanotube and its properties, okay, for example, it can withstand 6,000 watts per milli Kelvin at room temperature. It has a good high heat conductivity. Okay, its size is very, very less. It's very small, 0.8 to 1.8 nanometer. I mean, that's a size. When I look at density, it is about 1.4 gram per centimeter cube. Okay, it is when I look at its flexibility, it can be widely distorted without damage, and it can come back to its previous shape. So highly flexible. Okay, so it has a field emission. It has a very high tensile strength. It has a high thermal stability. It has a high current carrying capacity. When I make it into a carbon nanotube, so now I can put these special properties that the carbon nanotube acquires to various uses. So I can produce, for example, strong composites, I can use it as a sensor. I mean, I can use it in thin film transistors. I can use it as a transparent electrode. Okay. Uh, there are various properties of this carbon nanotube. Some are mechanical, some are surface area related, some are its electrical property, some are its optical property. I can use all of them for various purposes. Okay, so that's what carbon nanotube. When I specifically talk about, let's say, medical, health sector, in a carbon nanotube, for example, I can attach antimicrobial compound. Okay, so then what will happen is that when microbes interact with this carbon nanotube, that microbes are eliminated. Or I can use silver ions, which is a very high, very good antimicrobial property. Or I can even attach some polymer, carbon nanotube polymers, and then use them for example, let's say, if there is injury, covering that injury and things like that. Okay. One of the use, for example, people are looking at is that if I construct a drug carrier, okay, started with the carbon nanotube porins, okay. So then what will happen is that this drug carrier, these are all drug, okay. So inside this orange is a drug, okay, that can come and attach to the cell wall and then release the drug inside. So when the drug goes inside, the cancer cell can be killed. For chemotherapy cargo. Today, we are injecting chemotherapy drugs, so not only cancer cells but also good cells die off, right? So this kind of nanomedicine can give us a much more precision, uh, what you can call a drug delivery. That's a possibility that we have with carbon nanotubes.
Namaskar. My name is Samruddhi Sunil Mahajan. I am a pharmacy graduate and I am currently preparing for UPSC civil service examinations. My question is that what are the various types of vaccines, how are they prepared, and what is the significance and use of each type of vaccine? Thank you.
In today's context, when we are facing this pandemic, this is a question that we are all engaged with. So first, let us understand some basics of our immune system and how vaccines work. Okay, for a pathogen, okay, like let's say measles, there is a antibody. This already exists in our body. Why? Because we have contracted this measles sometime in our lifetime. Okay, so because of that, our body has produced antibody, which exactly fits the structure. For example, this and this fits, right? So if I look this and this, they fit. So they such kind of antibody is produced by our body. Or if I look at flu, many of us will get flu many times in our lifetime. So then there is antibody for it, which our body produces. Okay? Or chicken pox, right? So our body produces a antibody, which is exactly fitting the chicken pox. Okay, so this is called specific antibody. Okay, so these are all called a specific antibody. They are very specific to the pathogen. Okay, they are not general. So when a new pathogen we are encountering, like say for example novel coronavirus, we don't have antibody. Okay, so if it is something like flu, perhaps you may not worry too much because the chance of dying out of flu is comparatively less. But suppose if it is various kinds of pox, okay, or mumps, some of these kinds of diseases caused by pathogen, they are very fatal, and sometimes it comes in young children and then cause serious damage. You don't want to do that. Okay, so how do you make your body produce the antibody for that particular pathogen, even without actually contracting the disease? That's a question. Okay, so how do you do it? So when our body sees a disease-causing organism, our body produces antibody. So instead of giving the whole organism to my body, suppose if I give only one part of it, Or let's say I give a very weakened version of it, meaning that a version which cannot cause disease. Okay, either a part or a weakened version. Then my body will start producing antibody for that particular pathogen. So my body will produce the antigen even without actually the disease causing germ. That's vaccine. Okay. So what happens is that once the antibody is produced in your body, when the disease causing germ enters your body is able to fight that disease causing germ and then not make the disease severe. Some cases not even disease appear. Sometimes not even the pathogen take foothold. Uh, at the least, a vaccine prevents death and serious disease. Okay, that's what happens. So when I give a part of the pathogen or a weakened version, my body produces this new antibody. Once that new antibody is produced, as I said, that we are ready to face that pathogen. So if we are contracting it, then we will be able to fight it. So there are three major approaches in making a vaccine. Three approaches. Okay. One approach is what is called as using a whole virus or bacteria, okay, or whole pathogen essentially. Second is you use parts of those pathogen to trigger the immune system. You don't need the whole pathogen to trigger the immune system. Even parts are enough. That is where the antigens are. Okay. Or the third approach is, which is actually a very recent development because of the developments in biotechnology, is use the genetic material. Okay. So if the genetic material goes inside our body, our cells will use this genetic material, create the proteins of this pathogen. Okay, these proteins of this pathogen. Okay, this will be created in our cell. So once this protein is created in our cell, our body will create antibody. Okay, so that's what genetic material based vaccine does, right? So when you are looking at the whole microbe approach, that is whole pathogen, I mean, whether it's a whole virus or something, there are three possibilities there. Okay. I initially said that there are three approaches. In one of the approach, for example, when you are looking at whole pathogen, there are three ways you can use it. One is you can inactivate it, basically meaning that you cultivate that pathogen and use some chemical or heat. The genetic material degrades, okay, but the remaining proteins remain. Okay, so that is being inactivated, meaning that this pathogen cannot reproduce or cause disease. Okay, so but the body parts are available, so proteins are available, so our body can produce antibody for it. The second is uh, live attenuated vaccine. Attenuated meaning weakened. Okay, so it's a live virus, but it's a weakened version. Okay, so it does not cause disease. Okay, so that's a second approach. Mostly this is not the approach that we are taking today, because one, it is very complex to prepare and it takes time, and there are also risks associated with it. We don't usually go for this now. For example, there are no live attenuated vaccine for COVID. Okay, there is inactivated vaccine. For example, Covaxin is an inactivated vaccine. Then what we do is what we call as viral vector vaccines. Okay, so viral vector vaccine, what I do is that I take a simple virus which will not cause disease. Okay, maybe make a minor irritant, like for example throat infection or just a sneeze, things like that. Yeah, ordinary simple kind of virus, or a virus which affects let's say chimpanzee. That virus will not affect us. Okay, so I take that virus. In the gene, I add the genetic information related to, let's say, the one protein of my pathogen. Let's say in COVID case, I mean, we generally code the spike protein. So, okay, I have coded that spike protein in this gene. So, when this gene enters our cell will start producing this spike protein. So, once the spike protein is produced, that our body will produce the antibody for the spike protein without actually contracting the disease. For example, COVID, right? So, these are the three approaches. The other approach is we talked about the second approach, right, where we use the parts. That's called subunit approach. So in the subunit, I take only one protein produced by that pathogen and use that protein as vaccine. When this protein enters our body, that is our cell, our body produces antibody for it. Okay, our antibody produces antibody for it. But then this protein alone cannot cause a disease. Okay, so that's how we create the second approach. In the third approach, what we do is what is called as a genetic approach. What we do is that we take the genetic material of the pathogen, okay, suitably converted into either DNA or mRNA. Okay, then I enclose this genetic material in a lipid drop and then use it as a vaccine. For example, Pfizer is one such vaccine, okay, which is a genetic material approach based, right? So these are all the three major approaches in the vaccine making. Why we have many methods? Because we have many methods. We have many ways in which, for example, we can prompt our immune system to develop the right kind of antibody. So we want to try all of them. Okay, we want to try all of them. The attenuated vaccine, the inactivated vaccines, these were the earlier technology. Now with the biotechnology, we can try out some of these new methods like the genetic approach and protein approach and all that. So for many diseases, we want to develop vaccines as fast as possible. So these approaches help us in that, right? So that's how we use so when you look at a vaccine, the vaccine component will have an antigen and will have something called adjuvant. This adjuvant is to prompt our or prod our immune system to work, and there'll be some kind of a preservative so that the antigen doesn't decay, stabilize it to stabilize it. There'll be some surfactants, there'll be some dilutant, some residuals. All this will be there part of the vaccine. That's how a vaccine is produced. Yeah, it will be actually a cocktail. That's what will ensure that the vaccine works inside our body.
Hello everyone, I am Amit Chauhan, a science undergraduate student from Pathankot. My question is, what is immunity depth and how it has impacted humans? Why more and more people are falling ill because of COVID's immunity depth? Thank you.
Actually, this whole concept has come into public knowledge, and we are all talking about it because now there is a study that has come out from New Zealand. Okay, so let's look at what it is. Okay, so if I look around, there are various pathogens which are around. Okay, so it's not only coronavirus that's around. There are various kinds of viruses, various kinds of bacteria, various fungus. I mean, there are numerous that are around us, and every day, every minute, every second, they are entering us. Every time that you take breathe in that air that goes into your lungs, there is some pathogens. Okay, so it's not pure air. Remember that there is some pathogens wherever you are. Okay, whether you are in India, whether you are in some other place. Okay, air as pathogens. That pathogen goes through our nasal passage to, for example, lungs. So we are exposed to it. Okay. So as as we all know, when you talk about our immunity, okay, there is something called as active immunity and there is something called as a passive immunity. Okay. So first, let us understand what is passive immunity. Passive immunity is that when you are a small baby or other fetus in the mother's womb, you cannot produce antibodies, but you will need antibodies because pathogens may attack you, right? So what happens then is the mother produces the antibody and then gives it to the child via mother's milk. So even when breastfeeding, the mother is actually giving some amount of antibodies which are produced in mother's body to the child. Okay. Second is artificial, like for example, the plasma therapy, right? So from diseased people, you collect the serum and then give it as a medicine. Okay, so this is called as passive. Why this is called passive? Because this will work, this immunity will work only as long as these antibodies are there. you know that nothing in our body is permanent, right? I mean, blood, for example, blood cells live only for certain number of days. After that, the blood cell die, new blood cells come in, right? So similarly, every part, I mean, skin, for example, skin cells die, new skin cells are born. Similarly, antibodies, when they are produced, they will decay, and then you have to produce new antibodies. That's what will happen. So this passive immunity, once the antibodies decay, there is nothing left in your body. Okay, so it is only as long as the mother is feeding the baby that antibodies will be replenished, or only as long as you are giving plasma therapy, this will be replenished. Okay, so this is what happens in passive. When you are talking about active, okay, one is natural. That is when you are exposed to infection, your body produces antibody. Once your body produces antibody, then it remembers that antibody and that pathogen. Okay, so anytime in your lifetime, almost, okay, there are exceptions. Almost any time in your exception, when the same pathogen attacks you, your body will be able to respond with the antibody that was produced earlier. Okay, that's why most of the diseases caused by pathogens you get only once in your lifetime. I mean, if they are not fast changing. For example, flu is fast changing. So new and new strains come. So in fact, you have to say that you are attacked by different sorts of flus. Okay, it's not the same flu virus. They belong to your family, but they are not same. Okay, so that is the natural. The artificial is that you give vaccination. Through vaccination, you develop the antibody, so your body is ready to fight the disease. This is what happens. So, which essentially means the moment we are born, we are exposed to pathogens as babies, and we start producing antibodies. Okay, if you look at modern times, okay, modern times, I mean, we start producing antibody from mother's milk. We get some antibodies. Okay, and then infection and vaccination gives us some antibody. Our close interaction with pet animals, domesticated animals, gives us some antibody because they will transfer some pathogens. Okay, similarly, friends, relatives, so on will come and transfer. So when a baby is growing, the baby is developing number of antibodies for regular viruses. Okay, viruses which comes almost every year. Okay, there are seasonal viruses, seasonal pathogens which come. But then in New Zealand, when the pandemic hit this 2020, they had a very good lockdown. Okay, they had a very successful lockdown. That means they were able to control the spread of the COVID disease to a substantial extent. What is its side effect? A new baby which is born, that baby is exposed to maximum their parents, and the parents are not exposed to outside world because parents are not going there lockdown, so they are at home. So which means what the baby should be exposed in a normal course to ordinary pathogens that are around, the baby is not exposed. Now, when you open the lockdown, the parents go for work, or people in the baby's house go for work. They come back. They come back with the new germs, right? So the baby is exposed to those germs. The baby is not ready because baby has not faced it. Okay, so you have unseasonal attack of some of these germs. Okay, so that's what is called immunity dead, meaning that the immunity that the kid, the baby should have got by normal course, by interacting with others, playing with the animals, playing with the dog, cat, okay, or other babies, or going out to a park and then interacting with the people over there, through which, I mean, it should get many virus and germs. Because of the lockdown, the baby has not got. So there is a debt. Okay, so that debt is coming down now. So because of that, what is happening is that when the lockdown was lifted, what they found is that respiratory viruses like RSVs, okay, and influenza came in a big way with the children. Okay, that's it. That's what is immunity debt. it's something that should have routinely happened, but did not happen because of the lockdown. So now it is happening when the lockdown is lifted. Okay, so that's what is called as immunity.
My name is Gagandeep Singh and I'm a science student. So as of now, I am pursuing my graduation in Bachelor of Science from DOV College Secretariat in Chandigarh. My question is, what are rainbows are always in the shape of an arc rather than straight? And what is the anti-solar point in this concept? My second question is, what is the mechanism of science behind the quadruple rainbows? Thank you.
A long question, maybe we'll see at least some of them. Okay. So when you look at why a rainbow occurs, okay, so then you have to look at, for example, a raindrop. So, okay, a sunlight falls on that raindrop. So the raindrop acts like a prism, okay. So there is an internal reflection, and when the white light, that is sunlight, comes out, it comes out in Vigyan, or what we call as rainbow. Okay, so that's what is happening in a drop when you are looking at one light ray. Okay, when you are looking at one light ray. But suppose if I look at a white light, number of rays, okay, so when they all go inside and then they all come out, okay, each of them come out in different directions. So it's not only coming out in one direction. So one is coming out like this, one is coming out like this, right? So which means then actually it will make lots of cones of different colors like this, cones which are kept one another. So which means that actually a rainbow is circular. Okay, the actual rainbow that is formed is circular. Okay, so not only that one raindrop, there are also multiple raindrops which are forming this rainbow. Okay, so many of those rays also come to you. Okay, so that's how actually you see a rainbow, not only from one drop, right? So it never one drop is there. There are lots of drops, right? So what happens is that if I combine all of them together, there is a sunlight. So generally, the sun has to be behind you. Only then you will see the rainbow. So sun is behind you. You are here, and you see a rainbow. When at some distance there is either a cloud with the raindrops, or actually raindrops are falling. So okay, so then when the sunlight falls on those drops, they are dispersed. Okay, so then you get the rainbow. Very importantly, this is something that you have to note down. The rainbow, I mean, if you put a normal from you, okay, the rainbow is between 42 to 40 degrees. Okay, only when you are in that particular orientation, you will be able to see the rainbow. What is this 42 to 40? That 2 degrees is where you see all the Vigyan. That is different colors. Okay, so only when you are in that angle, you will be able to actually see a rainbow. Why? Very simple. Okay, so when I look at a sphere and light coming in, the angle at which it will come down will be 42. Okay, so it will be 40 and 42 between the blue line and red. Okay, that will be the difference. The red will be at 42, blue will be at 40. So when I say Vibjar, violet to red, it will be 40 to 42 angle. Okay, so when I am here, only when it is about 40 to 42 angle, I'll be able to see the rainbow. Okay, so I have to be in this particular orientation. Sun has to be behind, raindrop has to be at a distance, which will be at 45 degrees. So if the raindrop is somewhere here, then it won't be 45 degrees. So I won't see this rainbow. Okay, even if it is forming. Okay, that's something. So then why generally we see rainbows as an arc, not as a full circle? That's a interesting question people ask. Actually, you get a full circle. But suppose, assume you are able to see this full circle here because the earth is open here. But suppose if this whole area is filled with, let's say, mud, then what will happen? You will only see this portion, right? You will see only this portion. This portion will be behind the horizon, right? So it's below the horizon. So you think the rainbow is arc of a circle or a half circle, but it's not so. It's actually like this. So in this kind of special situation, you can see more than an arc. Sometimes you can even see the full circle. Okay, right? So the water is here, sun is behind you, so you are at a right place, which is about 40 to 42 degree. Then you will see the whole circle, rainbow as whole circle. Okay, so that's how it happens. This is how it happens. Okay, so the whole circle you are looking like this, because the water droplets in all these places are the water droplets from here are sending it out like a cone, so you are able to see it. Okay, so that's what is happening. So why do you see a double rainbow? Sometimes you can see a double rainbow when the water droplets slightly above, okay, around 52 to 54 degrees. Okay, so when they are above, okay, the first rainbow is about 40 to 42. That is a primary rainbow. The secondary rainbow is 42 to 52 to 54, because there is something called as total internal reflection can take place. So the sunlight can fall here, there can be a total internal reflection, and it can come like this. Here the sunlight is falling here and then it's coming like this. Okay, so here it is cycling and then coming back to you, right? So then you can have a secondary rainbow. But the interesting thing about the secondary rainbow, if you look at this order of color, it's a V jar, V to R, right? So it's here the other way around. V is here, R is here. Okay, so it will be inverted. Okay, the secondary rainbow will be always inverted, because it's going like this and coming back like this. Okay, so because of that, it will be inverted. That's one thing that you have to remember. Okay, so that's how if it is only a internal reflection, then you get it like this. If there is a double internal reflection, then you get like this. Okay, so that's how you get. Important part: suppose you and your friend are standing next to each other and are looking at a rainbow. Both of you are not looking at the same rainbow. There is a saying that no two-person sees the same rainbow, because the light coming to your eyes are light rays which are exactly angled at 42 to your eye. So your next person, the same light rays are not coming. Okay, forget about the next person. Your right eye and your left eye is not seeing the same rainbow. You can test it next time. So when you see a rainbow next time, so close one eye, look through your right eye, then close the right eye and look through your left eye. You will see the difference. Okay, so there'll be slight difference. When you open both, our brain combines both of them, create a composite image. Okay, so that's what happens. Okay, so that's something that you have to understand. So when you say quadruple or more than two, what happens? More than two, what actually happens is that, suppose if there is a primary rainbow, there is a secondary rainbow, and then, for example, something like a lake, okay, a lake nearby, which can reflect the sunlight. Okay, so then these two will be reflected. So you will see totally four. Okay, so you will see four rainbows. But suppose if in addition to a lake, uh, there are also something like a glacier, okay, sitting on the edge of the lake. Okay, then you can see six. Although it is physically possible, such situations are exceedingly rare, meaning that you have to be in a position where there is a lake and on the edge of it there is snow, and here there is raindrops and the sun is behind you and you are in the right place. All these things, if it happens, then you will be able to see six rainbows at one go. Okay, so this is what happens in the four rainbows are.
My name is Subham Kumar. Currently, I am preparing for UPSC. My question from Bharata first is: what are rare earth minerals? Why China has monopoly over it? How can India be self-reliant about rare earth minerals? And what is future of rare earth minerals? Thank you.
So if I look at a periodic table, uh, these elements are called as rare earth elements. Okay, so these elements are called as rare earth elements. Okay. Some of them are called as light rare earth elements, and some are called as heavy rare earth elements, because these are all heavy. In terms of atomic number, they will be heavy. These are all light. Okay, so these are two categories generally we use. Okay, so mm, so if you look at, for example, rare earth elements, right? So, for example, scandium is added to aluminium and you form a alloy. Okay, This is used in, for example, baseball bats, okay, bicycle frame. So if you want a very sturdy bicycle frame, this alloy gives us strength. Okay. So similarly, for example, if I look at Ethereum, okay, it's one of the rare earth element. Okay, it is combined with europium. Okay, so and that is what provides, for example, the color components in color television, right? Okay, cerium is used in, for example, in automobile to reduce the emission of sulfur dioxide. Okay, cerium breaks down the sulfur dioxide so that your emissions are safe, right? So like this, neodymium is used in it is used for permanent magnet. So cell phones, CD players, computers, loudspeaker, headphone, all of them have this. So if you look at the modern technology, if you look at electronic industry, whatever it is, mobile phone, computers, TV screen, that is rare earth element. And then rare earth element we are also using in creating new smart materials, materials, alloys with the other metal, so which becomes sturdy, harder, okay, rust free, various stuff, right? So rare earth minerals are used today in various areas. Like you are looking at magnets. When I'm looking at magnets, it's needed in computer hard drive. It's used in automotive part. For example, you are producing frictionless bearings using magnets. Okay, so for that you need rare earth element. Similarly, for example, if I just a few examples I'm looking at, like say for example ceramics, we use it in capacitor, but in the ceramic making, I mean we use rare earth elements, right? So like this, there are various applications in which we are using rare earth element in modern time. So it's one of the crucial elements in modern manufacturing. So if I look at rare earth elements who are having control, who are producing, okay, if I look from 1985 to 2020, so this red is of course China, and this blue is USA, and the white is the rest of the world. Okay, rest of the world including India. So you can see that around 2005 to about 2010, literally almost all the production was in the hands of China. But things have slowly changed in the recent past. Okay, one, the consumption has also come down slightly, and then the production in US and rest of the world has also picked up. Okay, so today, even today, but still, if you look at it, okay, the China alone produces 1 lakh 400 1 lakh 40,000 metric tons, but whereas the US production is just 38,000 metric ton, and the rest of the world is 62,000 metric ton. So add this, it doesn't even come to this. Okay, so even now China is producing more than 50% of rare earth elements. One reason is it has reserves, high reserves. Okay, and second is China has also entered into agreements with various countries which have rare earth elements for processing. So if you look at the processing, most of the processing actually takes place in Chinese firms or Chinese control firms. With regard to India, we have some rare earth elements, particularly things like, for example, thorium, which we are wanting to extract for our nuclear power project and things like that. Okay. So, but as a country, we don't have enough reserves of various kinds of rare earth elements which one needs for production. So, obviously, you'll have to look at imports, having some understanding with the various countries which have mines, so that we will have regular supply of this rare earth element. That's the current scenario.
Thank you, sir, for your insightful explanation of the questions. On this note, it's a wrap up of today's episode of Science Simplified only on Bharata First. Be scientific, be inquisitive. Please like, share, and subscribe to such amazing content on Bharata First. See you soon.